Okay, so we should really be looking for hospitals as loading. That might be a little bit actually could be in small blocks of flats. I'm just trying to find the hospital. Sorry, it's somewhere around here, but no, we're not looking for balconies, bedrooms. Oh, hospital wards. Okay, there we go. So category 8.3 perhaps will work for you. So you can take your area variable load as 2. And with that, you can calculate your loads. Okay, we're not doing museums. We're not doing that. It's fine.
Diana?
Yeah?
For the permanent load, we can pick whatever thickness the slab have?
I would start with 150. If you think that it's not sufficient, you can increase to 160, 170, but I think 150 should be fine.
Okay.
Okay. Yeah, sorry.
Yeah, because on the coursework guide it says 150.
It says on the first page. Yeah.
Yeah.
So 150 instead of 2 or 250 as it's given in this handout. Now, if you remember the lecture on the where are we? Over here. Sorry, switching between screens. It's fun. If you remember the lecture on T-beams, okay, we talked about we talked about our beams, and more importantly, the slabs on top. Okay, so we talked about how we can calculate the loading from the slab. So we can analyze the beam. Okay, so from area load, we then have to go into UDL that will be applied onto the beam. Okay, we need this so we can determine the loads on the beam and the reactions of the supports of the beam, so that we can determine our axial load in the columns. Okay, so we have the lecture on T-beam. Then we go into the lecture on columns. And then we go into the lecture on analysis. Technically, what you need to do, of course, you remember, if you have the span, which is roughly about 4 meters, I think I calculated as 4.5 for my example. The distance between the axes of the beams would be about 4.5. So each beam will take half of the load to the other beam, to the beam, let's say, on its left and on its right. So effectively, it will be supporting this strip of the slab. And the width of this strip would be exactly 4.5 meters. Okay? So if you have your area load, so let's say your 1.35 GK plus 1.5 QK is 12 kilonewtons per square meter. Okay? You need to multiply this with 4.5 so you can obtain your UDL in kilonewtons per meter. And then when you look at your beam, you're going to use this value to analyze the beam. Yeah? I think this is very straightforward. I mean, when you go through the lecture notes, you see that we've done this. So in the lecture on analysis, I'm actually talking about how we can isolate one of the elements of this frame that you see here, okay, this frame, so that we can find usually the bending moments, and for the columns, the axial loads and the bending moments. So you can use different subframes depending on whether you want to find the moments in the whole beam or only in one span of the beam, whether you're looking at a corner column or middle column, and so on and so on. So what I recommend to do is really to use this type of continuous beam analysis to find your reactions. This could be done using moment distribution. You remember how to do this from last year, okay? And then you also need to determine the moments in your column. So for example, if we are doing the column between level 1 and 2, we'll have something like this as a subframe. Okay, this is the column that we are after. And what we'll do is we'll place probably the permanent and variable load in the larger span. This is GD plus QD. I'm using the D to say that I've used the partial safety factors. And in the other span, I'm only going to use GD, although here you can use the characteristic permanent load actually if it's going to give you a greater moment at the joint. This again can be solved using moment distribution. I have shown you an example in the lecture. It takes one iteration, nothing complicated. So I don't think you're gonna have any problems.
The stiffness for the beams is halved.
Yeah, it is
Okay.
half exactly. So 1/2 EI over L. This is because this is more kind of realistic representation of the contribution of the beams in this analysis. If this is level 1 to 2, I'm happy if you have a fixed support at the bottom. If this is level ground floor to level 1, you could consider introducing a pin actually at the bottom and carry out the exact same analysis. The only difference is that in the first case, you're going to have a diagram that would be something like this, or the other way, depending on the loads. And on the bottom, you're going to have a diagram that looks like this, right? Because we don't know exactly what the foundation is going to be like, we could be a little bit conservative and say that we have a pin at the bottom. Probably in real life, because we're not exactly going to have the detail for a pinned connection like this, we'll have something between a pin and a fixed support. But let's say the ground conditions are a bit poor, so we're not going to be able to get this resistance to rotation at this level. So we can assume that we have a pin there as well. So this is also another variation which will make your project, your coursework unique. Okay. If you use a fixed support, I'm going to accept that as well, but I will put a note there that you could use a pin. Right. So with the reaction at this support and the moments from either the case with the fixed support or with the pin, we then can take our column and solve it. We can design it. This procedure is very straightforward. Okay, so you need to determine your L effective. It's you have a whole lecture on this, so you have handout. The steps are something like probably 5-6 calculations, nothing complicated. You just have to, of course, show me that you understand what you're doing. So L effective, in order to calculate your lambda and compare it with your lambda limiting. Now, lambda limiting is a function of 3 factors, a, b, c, and the square root of n. N comes from the loading, nothing on that side, nothing to worry about. But out of those 3 factors, a, b, and c, you need to find factor c. Okay, so have a look specifically at those slides and look at the video, the recording about the calculation of c. C can be less than 1.7. It could be equal to 1.7, or it could be greater than 1.7. So we want to have a say a conservative value for this C factor, so that we know if we have a stocky column or slender column. So we don't want to raise the value of C and therefore of lambda limiting too much and underestimate the actual slenderness of the column. I don't know if this makes sense. Okay, so if this is our threshold and we say that it's 30, that's going to be much better than overestimating it to, let's say, at 50 and saying, oh, our lambda is 42, so definitely we have a stocky column. But in reality, we might actually have a slenderness lambda equal to 25. So we'll actually have to, we'll have lambda equal to, let's say, 51 or 52. So that will make our column very slender. Okay. So it's important to spend some time looking at the calculation of the moments for the factor C. And once you have your factor C, you then feed it into lambda limiting, and then you design your column as a stocky column. Now, I would recommend to choose sections of your columns which will allow you to design them as stocky, to mean that there will be stocky columns. I think the example they have in the good guide is probably 300 by 300. If you're doing the column from the ground floor to the first level, so and level 1 to 2, I would start with 350 by 350. Okay, for maybe level 1 to 2, I'll go with 300 by 300. Usually, so you know, the dimensions of the columns remain the same for at least 2 floors, but in this example, we let's say have more freedom to change the dimensions of the column. Okay, if it so happens that you find that your column is slender, theoretically, you could design it as a slender column, but I would recommend to stick to a stocky column. The problem with the slender columns is that you have to determine some additional moments, and that requires several calculations, several iterations. So it's a little bit more time consuming. So by changing the dimensions of the column, technically you can avoid having a slender element. Okay. I think I said this in the presentation. If you're choosing the sizing, if you're choosing the sizes of the dimensions of your column, you probably want to go to the nearest 0, the nearest 5. So 300, 350, 400. But in this example, I will also accept 25s. So 325, 350, 375, and so on. If you think that this is more economical in that sense. All right, so I again highly recommend to choose sections which will give you a stocky column. Okay. After you've designed your column, really we are looking at a column with 4 bars at least, 1 bar in each corner. So you have your AS and you choose your 4, let's say 4H16 or 4H20. You wouldn't expect a very significant moment from this analysis, so I'll probably have the minimum percentage of reinforcement 4H12, 4H16, 4H20. Even 20 is probably very unlikely to happen, to be required. You will do the of course you'll determine the number of bars, the area of the reinforcement, and then you're going to draw some views, an elevation, cross section. I think, yeah, for columns that's more than enough. Of course, if you are working on a ground floor column, this column will come from the foundation. Okay, so let's say we have pad foundation. So if you have some reinforcement here on the bottom, you will have some starter bars. Okay, and you will have now the new bars from the new analysis. I've skipped the kicker here, but you'll see the drawings. And and then of course you'll continue to the top. I want to see the full height of the column and the connection to the lower level, to the level above as well. I want to see the links. Okay, so this would be more or less your coursework. I think there's a limit to the number of pages. What does it say? It said somewhere. Yeah, it does. 7 pages, including the drawings. I think this is perfectly doable. And I would expect your coursework to be handwritten, because I want to see that you have done the work. Hopefully, obviously, it's not a guarantee, but at least you had to write it on the to use a pen or a pencil to submit this work. I think, yeah, that's all we need.
Is there a
Are there any questions?
Is there a template for the coursework?
Oh, you mean like for the steel coursework?
Yeah, for the steel coursework.
If you want to use the frame that you get from the steel coursework, that's fine. But I would prefer if you handwrite everything rather than use Excel. This is because it's very tempting for one person to prepare this file and then send it to somebody else, and they use it, and it's still the work, still the effort.
Yeah,
yes, question.
A word written file explaining all the steps, would that be fine instead of handwriting?
I see. Well, the point of doing these calculations is really either to give you an example later on to use, especially for your group project, or to give you the opportunity to prepare like an Excel solution so you can use it again for any other courseworks, like, or group project or design or whatever. Now, if you all have the same Excel solution, I'll be very suspicious, because it literally just takes changing a few numbers to get the answer. But it wouldn't be fair to the people who have actually developed it. So I would say I prefer if it's handwritten.
Okay.
I know that it's a word, and it's going to look nice, but I still see sometimes students submitting the same type of file.
Okay.
Mm-hmm.
And is this lecture being recorded?
I started late, so there was no point. Oh, it has started. Someone is recording it. All right. But I'll record the one on Tuesday next week as well, because I'll go through the same thing, and I'll record from the moment we start the session.
My campus is personally not working, so I'm a little bit confused with those N numbers.
What's your K number?
It's 1735492.
Okay, so 1 is your N1, 7 is N2, and so on and so on.
Yeah, but there are no arrows. I can see it on my phone. There are no arrows as to where those numbers are referring to. But maybe it's okay in a computer, but for some reason I can't access Canvas on my computer.
Yeah, so you see it on the front page. Actually, use the. I have to update this then. Your K number is K1234567.
Yes,
So
yeah, I
that's
understand it,
technically
yeah.
N1, N2, N3, N4, N5, N6, N7. But even if you have the other kind of, even if you've taken a different N from the second page, I didn't see that one. Never mind. I'll accept it, provided that it's not too different.
Okay.
Yeah. If you have a 0, I think I mentioned somewhere you can take it as 1. I think I said it somewhere. So you can take it as 1. One additional thing here, guys. It's good to, I forgot. It's good to, of course, think about how the load is transmitted through the building. Why is it not? Okay. Because obviously this is a column. You have your frame, right? It's only 3 floors, but never mind. And you have a roof. And then you have level 3, 2, 1, and so on. You have to also decide what your roof is going to look like. So what kind of structure you're going to assign to the roof. This is because very kind of crudely, we have the loads from these beams going to the columns. Then we have the loads from these beams going into the column. Then the loads from these beams going into the column. So this is how we determine the loads on our column. All right. So this column here carries 1, 2, 3, 4 floors and roof, one level of the roof. This column carries 3 floors and of course the roof. Don't use helicopters, it's heavy. 2 floors and a roof, and so on. Okay, so if you have determined if you have determined loads from one of the levels, from the normal floors, can just multiply it with the factor to get how many floors this column is carrying above it, right? How many floors you have above this particular column, plus the roof. Do you know how to how to calculate the loads on the roof? Yes, of course. So you can choose a type of roof that you think is going to work for this type of structure. It could be flat roof. Probably it's going to be a flat roof, to be honest, because you see that the very last item that you have here is about the roof becoming an external terrace. So a place that the patients will visit, go out for coffee or for a smoke, whatever. Okay, yeah. So the last bit of your coursework, but of course we're not going there yet, is to think about how the structure of the roof will affect your column. Okay, this is the how to say, the open-ended question at the end of your coursework. It's where you have to prove your imagination. You have to use your ideas about the solution here. Something that our externals sometimes want our students to do. So yeah, 20 marks, but don't underestimate this point, because this is usually the decider between B and A. Question?
That external terrace, that would affect mostly QK. Is that correct?
When I say external terrace, it's more like a type of roof that will allow people to walk around and maybe
So
sit.
in terms of loading, it will affect the QK.
It will affect the permanent load and possibly the variable load a bit more, yeah.
Okay.
But again, you have to say, I'll suggest for this structure to, let's say, to change to another slightly different flooring system, and then load from, let's say, 12 kilonewtons per square meter will increase to 12.5 or 13 or 14 or 15. And then the loads on the column will increase as well. But you're probably going to have some spare capacity anyway, because I don't expect to actually for you to require to need reinforcement in the columns. You will provide it anyway, of course, because you need to build a cage. But obviously the bars will contribute to the work of the column with their compressive strength. So you can talk about the loading. You can talk about if you think it will change the slenderness of the supporting columns. You can talk about the design of the column, and so on and so on. The need for strengthening, for example. So you have to think how to answer, how to make your client happy, because things change as when you design your structures, either because of some mistakes on the construction site or some practical issues, or the clients change their mind. So this is this kind of situation. Any other questions?
Yes. Sorry, Dana. Earlier you were talking about the design of the T-beam slab and beam. I'm a bit confused. It doesn't really talk about it in the brief. Is that something we need to design for this, or can we not just assume a weight of the slab loading?
So your structure is a slab resting on beams. They're cast monolithically, so they're cast in one go. So you can say that your beams are T-beams or flanged beams. the slab contributes to the work of the beam. Now, you don't have to design the beam, you don't have to design the slab, but you do need to know how the loads go from the slab into the column. So you need to know how from one-way spanning slab to calculate the loads on the beams, and then from the beams, when you do the analysis of the continuous beam, using moment distribution most likely, you'll be able to find your shear forces, and with that you can calculate your reactions. So your total reaction for the middle support will give you your axial load in the column, but then remembering how many floors you have above that level, of course you have to use a factor of 3 or 4, maybe not 4, but 3 or 2 to find your actual n value. For columns, I'll probably expect something between, let's say, 1,400 and 2,000. It all depends kilonewtons for your column, depending on whether it's between level 1 and 2 or ground floor to level 1. Obviously, the ground floor one will be carrying the all the floors above it, so you get a value closer to 2,000. What else?
Are we including the self-weight of the T-beam?
Of course, yeah, that too. And don't forget the roof loading as well. I think that's what I wanted to say. Yeah. Yeah.
So with the analysis, you drew a little sketch of almost sort of like almost localized without the entire cross section of that part of the structure. Is that sufficient, or do we need to go further and analyze greater part of the structure? It's rather than just the two columns and two beams you sketched.
Well, if you look at the lecture from this week on analysis, you see that I talk about different types of subframes. I think that you find maybe a little bit the analysis a bit more challenging if you have more complicated subframes. So I've simplified the analysis to hopefully things that you know how to solve. So it's a continuous beam onto kind of on 3 supports, and you have a very short calculation for the subframe. So if you, of course, want to use a slightly more complicated subframes, I'm happy with that. You have options like where are we? Here, I'd say we're here. You'll have options like this subframe for the column and for the beam. You'll have the option to do this kind of analysis as well for the column to find the slenderness ratio. Okay, so let's say full load here, and just a permanent load in these to see how the moment in your column here will change depending on the position of the load. But if you don't have time for this, or you think that this is too complicated, then use the method I suggest: continuous beam and a small subframe.
Okay, thank you.
I know that obviously some of you have experience with software to analyze the whole structure, but the point here is to do a bit more manual calculation, so you kind of get a feel of the kind of how the different elements work. Mm-hmm. Question? Sorry, you were saying something?
I was going to ask what you literally just answered, so that's all good. Thank you, Diana.
Mm-hmm. All right.
So in terms of analysis, you are looking for how are we calculating the bending moments?
you have 7 pages, so you have to be you have to know how to use the available space. One of those pages will be the drawing with the column and the cross sections. So you technically have 6. So probably maximum 2 pages on analysis. And then, to be honest, the design bit shouldn't really take you more than 2 pages. So
Yeah. Yeah, that's fine. And for the self-load of the beams, T-beams,
yeah.
we can pick any dimensions that we want for those
Um,
T within the
right.
limits.
I think in the good guides, because this is the example that they solve in the good guide, but obviously it's slightly different because of the dimensions and the flooring system. They start with 250 by 450 for the beams, I think. So
Okay,
perhaps
that's
that would be a
fine.
good start.
Yeah.
So let's say, I think it should be all right with these spans, maybe a little bit. If you think that the beams should be 500, so let's say 450 to 500, and then 250. This could go up to 300 as well here. If you think that your beams need to be a little bit deeper, I think it should be all right. We might have some deflection problems, but we're focusing on the
Design
column
column.
design rather than the beam. Yeah.
Yeah.
There is. I talked a little bit about preliminary sizing of columns in the previous lecture. But again, 300 by 300 and 350 by 350 should be a good starting point. So what kind of loads you gonna? I want to see how you're going to design the roof. What kind of elements you're going to the roof technically is really your choice as a architect slash engineer. Of course, usually we'll have to consider waterproofing and soundproofing. Yeah, and thermal insulation. But I'll leave it to you to decide. I wouldn't recommend to make it a green roof because that weight is it could be actually heavier than the normal floor. But if you think that this is the better option, I'll just have to check to see if your design works for this kind of loading. So you can do that. It's just expect your loads to increase. Sorry. In the yeah, if you have a 0, take it as 1.
Okay, so where it says like I don't know, 3,500 plus 100 and whatever, you treat that as 3,500 plus 100 times 1.
Yeah. So your columns, the bottom column would be 4.5, 4 and something meters. Your other column, if you're designing level 1 to 2, should be 3,000 millimeters plus, so 3 meters something. It's just with the greater the height, the more likely it is for your column to be categorized as slender. So we have to be careful with the heights. But I think with this range, within this 3 to 4 and 4 to something, 4 to 5, it should be all right.
Okay, brilliant. Thank you.
Right. I think it's probably time to finish for today. Any other questions?
Yeah, Diana, for the effective length, obviously we have K1 and K2. If both ends are fixed, then K1 is equal to K2?
You're looking at the subframe for the bending moment in your column, right?
Yeah, and then I'm looking for the effective.
Yeah, no, the effective length.
Yeah.
The effective length you'll determine with the K factors.
Yeah, K1 and K2.
K1 and K2. So you see in the presentation we have the stiffness of the column divided by the stiffnesses of the beams at that end. So let's say for the top end of the column. So your K1 and K2, if the beams are the same size, I mean at the two ends of the column, the dimensions of the beams don't change. Your K1 and K2 should be the same, and your effective length should be between the full length of the element and about 50% of the length of the element.
Okay.
For that calculation, you can take the beam as rectangular, by the way.
Okay.
Rather than T-beam, because with the T-beam it will become a bit more complicated.
Yeah. So we're not looking at, so for example, if I was designing the beam, the column that was going from the ground floor to the, that was going from the basement to the ground floor.
Yeah.
On the ground floor, I will have beams, but in the basement, I'll just have a.
No, you can take it as a pin. Take it as a pin to the foundation. The rules are that, or the idea is that if you have a rigid foundation and you have the corresponding connection, you could assume that the bottom is fixed. But I think in the good guide, their foundation is pad foundation, and I think they assume that the soil is not very strong. So I mean the properties are not the best. So in that case, we can go with a pin. Again, the best thing to do is really to think about to express the kind of the stiffness of the foundation to rotation, so the rotational stiffness. But we're not going to go that way. So we can either assume that we only have kind of an axial load transmitted to the pad foundation, or we can say that if it's a fixed support, that we have a axial load and moment. But we don't have pad foundation in the example. It's a pad foundation, so I assume a pin is fine.
Right. Okay.
Yeah. Besides, if you have two fixed ends, that effective length would be shorter than the case when one of the ends is pinned. So it's a bit more conservative to kind of overestimate the length, the effective length. Mm-hmm.
Yeah. Okay, that's fine.
Mm-hmm. Right. So looking forward to your designs. I want to see. By the way, when you introduce your loads, I would prefer to see a cross section as well. So perhaps the flooring system, then screed, then the slab, then the suspended ceiling with just some characteristic loads, and then obviously the calculation of the design loads.
We can come up with our own numbers for example, insulation and thickness of screen, the type of flooring.
I would say, well, because it says that you're designing a hospital,
Okay.
I would prefer if you stick to the example given in the handout. But for the roof, you have several options, so it should be, you can use your imagination there.
Okay, and you said don't use the helicopter way?
Yeah, don't use the helicopter. It's I think it's a bit. Let's say that around the hospital, there's enough space for helicopter to land. So we don't need the roof for that.
Okay.
Okay. I think it's time to think about